Oh, welcome to the last tutorial. This week's, hi. So this week's general theme is finding the isomorphism type of a finite abelian group. So first we're gonna list all the abelian groups of order 360 up to isomorphism, then find the isomorphism type of Z8 plus Z4 mod, the subgroup generated by TUT52. And then we'll do problem 21 on page 221 of your textbook, which is also about finding isomorphism types. Okay, so list up to isomorphism means provide a list of groups such that every group in question is isomorphic to exactly one group in your list. I think my camera is not working. Oh well. Okay, so and then the way you do this is using the classification theorem. For finite abelian groups. So we prime factorize 360. So it's 2 cubed times 3 squared times 5. Then we write all possible ways. Oh, sorry, no, that's probably my fault. Okay, hopefully I have good internet. I mean, it's the last session. Hopefully the internet can come through. Okay, so we write all possible ways. And I don't know if you caught it when I said it. I think my camera is not working too for some reason. I don't know why. Everything's just malfunctioning. Okay, so we'll write all possible ways of splitting each prime factor, each prime power into a product of prime powers. So 2 cubed, you could just write it as 2 cubed, or 2 squared times 2, or 2 times 2 times 2. And 3 squared, you could write as 3 squared, or 3 times 3, and 5 is just 5. Okay, and then the final step is to form groups by combining the possibilities. So we can do Z2 cubed times Z3 squared times Z5. We can do Z2 cubed times Z3 times Z3 times Z5. We can do Z2 squared times Z2 times Z3 squared times Z5. We can do Z2 squared times Z2 times Z3 times Z3 times Z5. We can do Z2 times Z2 times Z2 times Z3 squared times Z5. And finally, we can do Z2 times Z2 times Z2 times Z3 times Z3 times Z5. Those are all the possibilities. And they're all not isomorphic. That's just part of the classification theorem for finite abelian groups. So it says that it'll always be a product of prime powers, and all the different ways of writing prime powers will give you not isomorphic groups. Note it's important to use distinct. It's important that we split into prime powers. That you separate the prime powers. Otherwise, you might get repetition in your list. So for example, Z30 is isomorphic to Z5 times Z6. So you really have to work with primes and their powers. Okay, item 2. Item 2, find the isomorphism type of Z8 plus Z4 mod 22. Okay, so first we'll list the elements of Z8 plus Z4 mod 22. My bad. The first thing I did was find all groups of order 360 up to isomorphism. Not the possible isomorphisms, but the possible groups it could be isomorphic to. So it's just all the way of splitting 360 into, so first of all, 360 is 2 cubed times 3 squared times 5. And then you just have to figure out for each prime power, what are all the different ways you could split it. So 2 cubed can be 2 squared times 2, or 2 times 2 times 2. 3 squared could be itself, or 3 times 3. And then combining all those possibilities gives you 6 options. Yeah. Do let me know whenever you want me to go back. It's no problem for me. So first we'll list just the elements. The elements are cosets of 2, 2. They're cosets of the subgroup generated by 2, 2. And then what is a subgroup? So 2, 2, the subgroup has 0, 0. It needs to have the identity. It has 2, 2. It has 2, 2 plus 2, 2, which is 4, 4, which is equal to 4, 0. And then it has 6, 6, which is equal to 6, 2. Okay, I'll just write 4, 0 and 6, 2. And that's it. Okay, so now we'll list the cosets. So the cosets are, there's 0, 0 plus 2, 2. And that's just the subgroup itself. There's 1, 0 plus 2, 2. 2, 0 plus 2, 2. And 3, 0 plus 2, 2. 5, 2, 7, 0, 1, 2. Okay, and then we've covered 4, 0 plus 2, 2. It's the same thing as 0, 0 plus 2, 2. We've covered 5, 0 plus 2, 2. It's the same thing as 1, 0 plus 2, 2, 6, 0, and so on. We've covered 2, 2 plus 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 2, 0, 2, 1, 2. So we've covered all the elements with second coordinate 0 or second coordinate 2. So let's get some with second coordinate 1 now. So we'll do 0, 1 plus 2, 2. That's going to be 0, 1, 2, 3, 4, 1, 6, 3. And then we'll do 1, 1 plus 2, 2. So that'll be 1, 1, 3, 3, 5, 1, 7, 3. We'll do 2, 1 plus 2, 2. So that'll be 2, 1, 4, 3, 6, 1, and 0, 3. And then this is the last coset. So, and to make sure we're done, remember that Z8 plus Z4 has 32 elements. And we've written 8 disjoint cosets size 4. And 8 times 4 is 32. So we're good. All right, now the next step is to find the orders of the elements. Okay, so we'll look at, well, the identity is easy. So we'll look at 1, 0 plus 2, 2. So there's 1, 0 plus 2, 2. Then 2 times 1, 0 plus 2, 2. What I mean is 1, 0 plus 2, 2 plus itself is 2, 0 plus 2, 2. 3 times 1, 0 plus 2, 2 is 3, 0 plus 2, 2. And then lastly, 4 times 1, 0 plus 2, 2 is 4, 0 plus 2, 2. But then since 4, 0 belongs to the subgroup generated by 2, 2, this is actually just equal to 0, 0 plus 2, 2. So this implies okay, so therefore we've shown that one 0 plus 2, 2 has order 4. And actually, if you recall, in a cyclic group, you can figure out the orders of all the elements. And so all these other elements I've listed, they belong to the cyclic subgroup generated by 1, 0. So we know the orders of all of them. So since all the elements above belong to the cyclic subgroup I could just figure out their orders by scratch. That's fine too, but I'm lazy, so I'll look for a shortcut. So they all belong to the cyclic subgroup generated by 1, 0 plus 2, 2. So we can figure out their orders. With very little extra work. So 2, 0 plus 2, 2 has order. I'll just use the formula 4 over GCD 2, 4, which is 2. And 3, 0 plus 2, 2 has order 4 over GCD 3, 4, which is 4. Okay, that covers half the elements in our group. So we still have the cosets that end in 1. So 0, 1, 1, 1, 2, 2, 2, 1, 3, 1. Okay, so for 0, 1 plus 2, 2, if you add it to itself, you get 0, 2 plus 2, 2. And that's actually a coset we've already done. It's the same thing as 2, 0 plus 2, 2. And then 3 times 0, 1 plus 2, 2 is 0, 3 plus 2, 2, which is one of the cosets here. Same thing as 2, 1 plus 2, 2. And then finally, 4 times 0, 1 plus 2, 2 is 0, 4 plus 2, 2. Which is, 0, 0, because we're doing Z8 plus Z4. So this is just 0, 0 plus 2, 2. So therefore, 0, 1 plus 2, 2 has order 4. And it follows that 2, 1 plus 2, 2 has order 4 over GCD 3, 4, which is 4. Okay, so that covers 0, 1, and 2, 1. There's still 1, 1, and 3, 1. So 1, 1 plus 2, 2. If you do 2 times it, you get 2, 2 plus the subgroup generated by 2, 2, which is 0, 0 plus 2, 2. Okay, so it has order 2. Now, if we look at the last element is 3, 1. So 3, 1 plus 2, 2. If we do 2 times it, we get 6, 2 plus 2, 2. And that's the same thing as 0, 0 plus 2, 2. Okay, so 3, 1 plus 2, 2 has order 2. Okay, so we already know what our group is actually. So none of the elements in our group had order 8. So it's not isomorphic to Z8. Because the element 1 in Z8 has order 8. Also, Z8 plus Z4 mod 2, well, it had elements of order 4. Okay, you know what? I'll just directly apply the algorithm. No, okay, I'll finish what I was saying, but we could just directly apply the algorithm too. But anyways, I'm just saying how we can already figure out what the isomorphism type is. But there's a second thing is to actually write it as an internal direct product. But for now, I'll just figure out what it is. So we had some order 4 elements. But Z2 plus Z2 plus Z2 doesn't. Hence, it's not isomorphic to it. So there's only one possibility left. Which is that it's isomorphic to Z4 plus Z2. But we could have directly followed the algorithm. So like what happens when we follow the algorithm? So first, we find an element of maximal prime power order. So that'll be all the orders we got. The orders we obtained were were 2 and 4. So 4 is the maximum. So let's look at a random one of order 4. For example, 0, 1 works. Okay. Now 8 divided by 4 is 2. So now we look for an element G such with order 2, but there's an extra condition. Yeah, it has to be prime power. So it's an element. Yeah, it could happen. It could happen. So Z5 times Z6 has an element of order 30. But you find the one that's the largest prime power. So like if you had like 30 and 5 and 6, oh wait, 6 is not a prime. So I guess I should write times Z2 times Z3. But yeah, if you had 35, 2, and 3, then 5 would be the largest. So it's the maximal prime power order. I'll make a note of that. Okay. So now we're going to look for an element G that has order 2, and there's an extra condition. So we don't just take any random element of order 2. The extra condition is that G is not in our current subgroup. So it's not in the subgroup generated by 0, 1 plus 2, 2. And that's equivalent to saying that G does not equal 0, 0 plus 2, 2, 0, 1 plus 2, 2. What are the other powers of 0, 1? So there was 2, 0 plus 2, 2. And then there's 2, 1 plus 2, 2. And this is equal to, well, just to show how I got these. So this is 2 times 0, 1 plus 2, 2. This is 3 times 0, 1 plus 2, 2. Okay, so any element of order 2 that, so any element of order 2 that isn't one of those, so for example, what are some order 2 elements we found? So we can't take 2, 0. We can't take 0, 1, 2, 0, or 2, 1. So we can't take 2, 1, 2, 0. Okay, so we could take 1, 1, and 3, 1. Those are our possibilities. So I should just write IE, not example, because those are the only ones. And then after that, we're done. So then we get Z8 plus Z4 mod 2, 2. It's equal to an internal direct product of 0, 1 plus 2, 2, the subgroup it generates, times, and then you can do 1, 1 plus 2, 2. It's also have, you could have also did 3, 1 and it would still work. So yeah, those are the 2 possibilities. Any questions? I can always go back. Oh, yeah, good. So then there's the last one is problem 21 on page 221 in your textbook. So there's this weird group. So we'll let G be the group 1, 16, oh no, 1, 9, 16, 22, 29, I think, 53, 74, 79, and 81. Under multiplication, mod 91. And then the question is to find the isomorphism type. So note that G is abelian. That's why we can find its isomorphism type. Okay, so we'll find, the first step is always to find the orders of the elements of G. Actually, no, well, first I'll say, since G has 9 elements, we already know it's either Z9 or Z3 plus Z3. Okay, so first we'll list and maybe I think I forgot to write something. Oh yeah, so when I'm writing this internal direct product, I should say that the first thing in the product is isomorphic to Z4, and the second thing is isomorphic to Z2, because the first one was had order 4 and the second order 2. Same thing here. So that's why So that's why, so we do end up getting that it's isomorphic to Z4 plus Z2. Okay, back to this question. So first we'll list the orders of the elements of G. Okay, so 9, there's 9, then 9 squared is equal to 81 mod 91. And then since 81 is negative 10 mod 91, 9 cubed is equal to 9 times negative 10, which is negative 90, which is 1 mod 91. Okay, hence, and this negative trick is useful only if like situation like mine, you need to do mental math. Otherwise, you could just do 9 times 81. That's fine. Okay, so 9 cubed is equal to 1 mod 91. So 9 has order 3. And then it follows that 81 has order 3 over GCD 2, 3, which is 3. Okay, now let's look at next element, 16. 16 squared is 256, which is 182 plus 74. So it's 74 mod 91. And then 16 cubed. Well, since 74 is equal to negative 17 mod 91, 16 cubed is 16 times negative 17, which is negative 272, which is negative 273 plus 1, which is 1 mod 91. So 16 has order 3, and it follows that 74 also has order 3. Because it's a power of 16. And you can figure out, if you know the order of G, you can figure out the order of G to any power. Okay, so it has order, and this is like a theorem we learned. 3 over GCD 2, 3, which is 3. Okay, the next element is 22. So it's 22, 22 squared is 484, which is 455 plus 29, which is 29 mod 91. Then 22 cubed is 22 times 29, which is 638, which is 637 plus 1, which is 1 mod 91. So 22 has order 3, and it follows that 29 has order 3 over GCD 2, 3, which is 3. And finally, there's, what was the last one? Where did it go? Oh, 53. So 53 squared is 2809, which is 2730 plus 79, which is 79 mod 91. And then 53 cubed. Well, I can write 79 is equal to negative 12 mod 91. So 53 cubed is 53 times negative 12, which is 636, negative 636, which is negative 637 plus 1, which is 1 mod 91. Okay, so 22 and 79, I mean 53 and 79 have order 3. Okay, so no element of G has order 9. Hence, G is not isomorphic to Z9. So G is isomorphic to Z3 plus Z3. But if we use the algorithm, we can figure out, we can actually write it as an internal direct product. So first, what is the highest what is the maximal prime power order in G? Three? Yeah. Good job. So every element had order 3. So it's 3. And we could just take any element of order 3 for the first step. So we'll take 9. And then 9 over 3 equals 3. Okay, I don't want to confuse this 9 with the other 9, so I'll take 16 instead. Okay, so 9 over 3 is 3. So now we look for an element G. Again, it should have order 3, but there's an extra condition. But we want G and G squared to both not be in the subgroup generated by 9. So, which is equivalent to saying that G and G squared, they're both not equal to, well, I'll just write not in the set 1. Oh, I took 16. So it'll be 1, 16. Right. Let me just write the last element of 74. So the significance just tells us how many elements we have left, kind of, in the product. Like, so like we're trying to write it as a product like Z5 times, I don't know, Z5 times Z2 or something. If we find this first Z5, then we have to account for 10 in our product now. So like for, it helps narrow down the possibilities. So for, it's not that useful in the examples. I didn't pick these examples to do, but for example, if you had, it's not that useful of a step actually. You actually don't need to do it. So you could just look for an element of maximal prime power order that all its smaller powers don't belong in your subgroup. This could just narrow your search down a bit. Like, for example, I don't know, if you found an element of order 8, and the total order was, let's say, 32, then 32 over 8 is 4. So you don't need to look at elements of order 8. In the next step. Because you only, you know, it's either going to be 4 or 2. Of course, this isn't actually like, this isn't strictly necessary, because either way, if you just looked at every element and looked at what power ended up in your group, all the ones that have order 8, some smaller power of them will end up in the group. So either way, you would not need to, you'll know that the elements, like, this only saves you time. You wouldn't go wrong by not doing this. But yeah, it could save you time. So like if you found an element of order 8 and your total is 32, you know that in the next step, it's not going to be another element of order 8, because it's not going to be like Z8 plus Z8. That's too much elements. So yeah, that's the point of that step, but it's not strictly necessary. It's just for efficiency. Oh yeah, so we're looking for an element such that G and G squared are both not 1, 16, 74. Every element except 1, 16, and 74 works. Because all our elements have order 3, And all of them, when you take it or its square, it doesn't end up in the set. So G equals 9, 22, 29, 53, 74, no, not 74, but 79 and 81 all work. So we can write, so as an internal direct product, we can write G equals 16 times 9, it equals 16 times 22, G equals 16 times 29, and so on. And in each case, this is isomorphic to Z3 because they have both factors of order 3. This is isomorphic to Z3, this is isomorphic to Z3, this is isomorphic to Z3, this is also isomorphic to Z3. Okay, so that's actually all that we were supposed to do this week. I'm curious if there is an example in the textbook where the greedy algorithm needs 3 steps, because I feel like in the 2-step ones, you don't really see what's going on. But I wasn't prepared for this because I didn't know I'd finish earlier. But let me see. Maybe. Yeah, I think all of them are 2 steps. There's no like, I don't know if you can find one, let me know, but all the ones where you actually have to apply the algorithm end in 2 steps, which is, I guess, good because if you had to do a 3-step one, it would be super annoying. Yeah, so I guess I'll just end off here. Yeah, or unless you want me to do an example, you can suggest one to me if you like. I just meant like from the textbook, like an exercise, but if you don't want, it's fine too. Like the exercise is in chapter 11. I can do a random one in like 5 minutes, maybe. Okay. All right, then. Thanks for coming. It's been a pleasure. And yeah, I wish you all the best. Bye.